Okay, so this is the second lecture on chapter 10. So I'm gonna, maybe I'll share the screen already. Okay, where are we here? So just to review a little bit. How many reasons of electron density are around this central atom right here?
4.
Exactly. How many reasons of electron density are around it now?
4.
Still 4.
Okay.
Right? And so when I had all the atoms on here, the shape was tetrahedral, right? Because these 4 reasons of electron density want to be as far apart from one another as possible because they repel one another. Electron clouds repel one another. This is the reason why matter tends to be symmetrical. Now this particular one is, the shape is now described as pyramidal. This particular one is described as being bent. But the reason why it's bent is because these reasons of electron density are repelling the other reasons of electron density. Okay? What is this shape?
Bent.
No, it's just diatomic. There's only 2 atoms. So there is no central atom. So the shape is just diatomic. This one has 3 atoms on it. So it is bent.
Excuse me, Professor. Can you remind me what's the difference between in that toy that you're holding? What's the difference between the connections with the atoms on it and the ones without it? I mean, they're both electrons, right?
Right, exactly. But I will point out, Michael, that this is not a toy. This is a very valuable tool.
The model.
Yeah.
I was trying to find the right word.
Okay, but I like that because, you know, some of my friends and I were like, borrow tools from each other all the time. And it's like, well, you know, these are really toys. We like to play with it, even though we're grown men. When you get older, they're not tools anymore. They're not toys anymore. We call them tools, but in fact, they're still toys.
My mistake.
Yeah. So anyway, I'm not sure exactly what you're saying, but if you look at this shape, this is bent. That's a reason of electron density. So is that, so is that, so is that. So there's 4 reasons of electron density. But what we really care about is how the atoms are situated to each other. That's where we get the shape.
So the white balls on either end, I mean, they're atoms. They're not just electrons.
Yeah, they're atoms. Yeah.
They're atoms. Okay, so it could be, one could be chloride and the other could be nitrogen, and then you have 2 electrons on the top of the black atom.
Those are electron pairs. Exactly.
Electron pairs. Okay. Okay. Thank you.
Mm-hmm. Also, let's just review this one. So here I have 2 central atoms. This one right here has 1, 2 regions of electron density, 2 reds. Now to keep those reds as far apart from one another, you get this linear situation, right? That's linear. This other central atom over here has the same situation. So it's linear here, and it's linear here. This is a linear molecule, in fact. This one here has two central atoms. This one is a central atom, and it has 1, 2, 3 reasons of electron density. So it's planar, which means it's flat, and it's trigonal. So we call it planar trigonal. This one here has a similar situation, right? So this molecule itself becomes planar trigonal in 2 different places. Then if I could my other one, oh here. So this one has a slightly different situation, but both of them have 2 central atoms and they're both planar trigonal.
What are the black balls on the outside? Are those atoms or are those electrons or are the
Those are all atoms. They're connected by electron clouds, right? Valence electron clouds, and every ball is an atom.
Gotcha. So even the white ones on the other molecule?
Yep, those are all atoms. Okay, so the last thing we talked about was difference in electronegativity. And we first encountered that in chapter 5, and I've talked about it in several cases. So when we take the difference in electronegativity, that puts that particular bond, that numerical difference, put that particular bond into one of 3 categories. And I went through the reasons, the logic for doing that, but you're just going to have to kind of remember these, 0.5 and 1.7, okay? And so if it's less than 0.5, we don't do anything. If it's greater than 1.7, it's considered an ionic bond. And if it's anything in between, then we call it a polar covalent bond. And we put the polar markings on there, which are the partial charges. And again, if I'm looking at chlorine and I'm looking at hydrogen, the one with the largest electronegativity is chlorine. So electrons are being pulled away from the hydrogen towards the chlorine, giving chlorine a partial negative, and hydrogen a partial positive. Okay. So in this case, it's a partial charge. They're still being shared, but they're shared unequally. Over here, we pretend like the electron is completely transferred and it's an ionic bond now. And we have full charges. And the reason why I say pretend that is because the cutoff value is really if it's greater than 50% ionic character. Say it's 51% ionic character. Well, the other 49% is covalent character. So we looked at how to put them onto bonds where it's deserved and where it's not. So the carbon to hydrogen bond is only 0.35, so it's not, it's a non-polar covalent bond. Doesn't really affect the behavior of the molecule. This one right here happens to be 0.89, so it's a polar covalent bond. We put the partial charges on it. Now you can see that's going to affect the behavior of that molecule. That's behaving like a little magnet. Water's a magnet, isn't it? So now, based upon what we just did here, could you tell me, does formaldehyde dissolve in water? The answer is yes, because they both are little magnets, and little magnets are attracted to each other. So anyway, moving on a little bit, going a little bit deeper into bonding. we now have 3 categories of bonds based upon the individual characteristics of each atom. This is way more precise than saying, oh, this is from one side of the periodic table, this is from the other side of the periodic table. One's going to be positive, one's going to be negative because of that location on the periodic table. And we had only 2 categories, covalent and ionic. Now we have 3 categories based upon the individual properties of each element. So this is way more precise. So here's the reason why I chose less than 0.5. Here's the reason why I chose greater than 1.7. And here's the other thing. I put this line over here to show you that we may have completely white because the different electronegativity can be 0, but it never gets dark. It never gets black. It's simply grades of gray. It gets more gray and more gray and more gray. And here's an example of that. So bonds between metals and nonmetals are not necessarily ionic. For example, if we take tetraethyl lead, here's the formula for it. That was previously used in leaded gasoline. So what does that mean? Does gas dissolve in water? No, it does not. So if this molecule right here has a metal and nonmetals, it dissolves in gas, it doesn't dissolve in water. So what that means is that this molecule right here is behaving like it's not a magnet. And if we look at the difference in electronegativity between lead and the carbon, it's only 0.22. You know what that does? That really makes it as a nonpolar covalent bond. So there's little or no charge on tetraethyl lead, which is why it dissolves in gasoline and not water. Then bonds between nonmetals are not necessarily covalent. So for example, hydrogen fluoride. It's 2 nonmetals, right? But the difference in electronegativity is 1.78, making it 55% ionic character. It's really acting like it's an ionic bond. That explains some of the weird properties of hydrofluoric acid. We use that to dissolve glass. That's what they use to etch glass. Glass is an ionic substance. So is hydrofluoric acid. That's why they dissolve in one another. Then sodium chloride, which you've grown up with. I don't know when you first learned about sodium chloride, but my 7-year-old grandson knows about it. But not sure the parents do. But anyway, the difference in electronegativity is 2.23. So if you go to the top of the periodic table on side 2, right? You read electronegativity across this way and then straight down to get the percent ionic character. This is 71% ionic character in sodium chloride. So what is the other 29%? Covalent character. So what? Sodium chloride is not completely ionic? Yes, that is the case. So if I were to take a solid chunk of sodium chloride, it is not a very good conductor of electricity because it isn't a completely ionic substance. However, if I melt the sodium chloride, I am forcing the electron to go completely from the sodium to the chloride. Molten sodium chloride is an extremely good conductor. Or if I take sodium chloride and dissolve it in water, again, I'm forcing the electron to go 100% from the sodium to the chloride. It now becomes a very good conductor of electricity. So Polar versus non-polar molecules. We use electronegativity in the molecular shape to determine if the molecule is polar. So this has to do with vectors. So let me ask you a couple of questions. Look at this molecule right here. Is this molecule symmetrical?
Yes.
It is. So say this was a rocket right here, and this was an equal rocket, and I have them in opposite directions. I fire those two rockets at once. Is this going to go anywhere? The answer is no. Therefore, it's a non-polar molecule. Now, what determines if this actually is a rocket or not? The difference in electronegativity. Okay? If it's a polar covalent bond, we can treat it like it's a rocket. If it's a non-polar covalent bond, then it's not even a rocket. So in order for a molecule to be polar, in other words, to effectively dissolve in water, behave like a little magnet, it has to have rockets, which means it has to have polar covalent bonds, and it can't be symmetrical. So this is a non-polar molecule. This molecule is not going to dissolve in water. It doesn't matter whether that's a rocket or that's a rocket. It doesn't matter. It's not going to dissolve in water. So what about this one? Say all four of these were rockets. If I fire all four of these rockets, where's it going? Nowhere. This is a symmetrical molecule. It's never going to be a polar molecule. Now, what if I take off one of this? Is this symmetrical? No,
Yes.
it's not.
No.
If these three are polar covalent bonds, if these three were then rockets, if I fire these rockets, is it going to go somewhere? It's going to move, isn't it? That means that if these are polar covalent bonds, this is a polar molecule and will dissolve in water. If they are not rockets, if they're non-polar covalent bonds, there's nothing to fire. So it's not going to dissolve in water. Rather, it would dissolve in oil.
Excuse me, Professor. When you say they're rockets, are they all pointed towards the center?
It doesn't matter. Whether the rockets are going this way or that way, it doesn't matter. If they're the same and they're rockets, it's going to move. So here's situations where the dipoles cancel. Okay, these are non-polar molecules. Here's where the dipoles don't cancel. Okay. So let's look at carbon dioxide for a minute. Determine if carbon dioxide is a polar or non-polar molecule. So we're going to put a lot of things together right now. So here's the formula. Now we have to decide which will be the central atom. I would predict carbon. So that's what I'm predicting. But then to prove it, I have to count up all the valence electrons. So there's 16. And then I put them first into the bonds, then to the outer atoms, right? And then I look for happiness. So here's 8. That oxygen's happy. This one's happy. What about carbon? Has only 4 around it. Carbon is not happy. So what do you do if you have enough valence electrons for yourself and your very, very close friend doesn't? Well, you share, because we live in the Hello Kitty world. Everything is happy. So here I took these non-binding electron pairs, put them into the bond in an effort to give carbon more valence electrons. So right now it has 2, 4, 6 around it. It's still not happy. But in this case, it helps to have another friend. So now if I share these over here, notice that I've made every single atom in there happy. Carbon has 8 valence electrons around it, symbolizing S2P6. So the bond angles here, 2 regions of electron density is 180. Well, let's find out whether these bonds here are rockets or not. So the difference in electronegativity, 3.44 minus 2.55 for carbon is 0.89. That's in the category of being a polar covalent bond. We assign charges. These are rockets. So the more electronegative atom is oxygen, so it gets the negative. That means carbon gets the positive, and the same thing over here. And now look at carbon dioxide. It has polar bonds. It has rockets in it. But is it a polar or a non-polar molecule? Somewhere ahead. Here. So I got 2 rockets. If I fire these 2 rockets, where does it go? Excellent answer. Nowhere. So that means that carbon dioxide has polar bonds, but it's behaving like a non-polar molecule. It does not behave like a magnet. This is the reason why carbon dioxide is a gas. Does that make sense to you?
Why? So oxygen is more electronegative. I understand that because you can look at the table and see that. But how do you know it goes outward?
Because the one with the greater electronegativity pulls electron clouds towards it, and electron clouds are negatively charged.
Gotcha.
Mm-hmm. So think about that. This is a very important molecule to understand. Carbon dioxide is a gas. That means it has very weak attractive forces. Okay. Why? Because it's a non-polar molecule. Why is it a non-polar molecule? Because it has rockets in it. It's because it's a symmetrical molecule, and all the rockets just cancel each other out. Another way of saying that is that there is no net dipole. Dipole here, a dipole here, in equal and opposite directions, so they cancel out. Let's go back to formaldehyde for a minute. So remember how we put the partial charges on here and these didn't get partial charges? Is there a net dipole in formaldehyde?
Yes.
There's one rocket, nothing there to cancel it out. It's a polar molecule. It dissolves in water. When you take formaldehyde and dissolve it into water, you get a solution that's now called formalin. And I see a typo right here. I'm going to correct this since I decided that I can do this. So in summary, and I tried to summarize many different ways because this is a complicated thing, and I realized that too many summaries, this causes more confusion. But if there are no rockets, the molecule is nonpolar. like oxygen, right? Difference electronegativity is 0. If there's only one rocket, the molecule is polar, like formaldehyde. If there are more than one rocket, the molecule might be polar. So what do we have to do? Look at the number of reds, get the shape of the molecule, put charges on the polar bonds, those are the rockets, then look at how they're orientated in space. If the rockets don't cancel, the molecule is polar. If the rockets are symmetrical, they cancel and the molecule is non-polar. For example, carbon dioxide. And if there's full charges, the molecule is ionic, which simply means very, very polar.
How do we determine based on, we don't have a model to use, so how do we determine that they're symmetrical or non-symmetrical?
Well, most of the time oftentimes I will give you the shape, but in some cases, for exam 3, you'd have to figure that out.
Okay.
But in some cases, I would just show you a picture of the model.
Mm-hmm.
So first you get the Lewis structure. It's either symmetrical or asymmetrical. You get that shape from the number of regions of electron density. Then we look at the difference in electronegativity. So if there's non-polar bonds only, it's a non-polar molecule. If there are polar bonds, it might be a polar molecule. But notice that this is because it's asymmetrical over here. You have to be asymmetrical and have polar bonds for it to be a polar molecule. So carbon dioxide had polar bonds, but it wasn't a polar molecule because it was symmetrical. So you'd be going this way, right?
Would the same go for H2O?
H2O, you up here, oh, it's unsymmetrical. Does it have polar bonds? Yes, polar molecule. Formaldehyde, unsymmetrical. Is there polar bonds? Yes, it's a polar molecule. So yeah, this does take a few readings for it to start to sink in. No question about that. It's one of the more difficult things you're going to encounter in chemistry. So anyway, we can look at a lot of different things, and polar molecules have relatively strong attractive forces, have higher melting points, higher boiling points, higher surface tension, higher heats of vaporization, higher specific heats, lower vapor pressures. That's what we're going to be covering in those chapters over there. And polar molecules are likely to exist as a solid or a liquid at room temperature. Non-polar molecules would more likely to be a gas. Polar molecules dissolve in polar solvents, but not in non-polar solvents. So if you look at textbooks, including what you're going to find on the internet, whenever they come to explain something like this, they just say, oh, like dissolves like. But this does not explain it. All it does is describe it. And it's irritating to me. Like dissolve likes means that polar molecules dissolve in polar solvents, non-polar molecules dissolve in non-polar solvents. But don't you need to know why that is instead of just memorizing that term, like dissolves like? You now have the ability to find out whether a molecule is going to be a magnet or a non-magnet. Non-magnets behave like, to me, polar molecules that are behaving like magnets are attracted to other magnets, stronger attractive forces. Non-polar molecules don't behave like magnets, so they're going to have weak attractive forces to everything. So let's look at this picture of the real world. Sorry to bring up the real world to you. I know it's something you're trying to escape from by going to college, but occasionally we do talk about the real world. So here's water and here's oil. You know that oil and water don't mix. Well, now we're going to try to understand that. Water molecules, we said, were polar. They're like a whole bunch of little magnets, and they're all stuck to each other, right? Oil are non-polar molecules, and they're not attracted to each other because they're not like little magnets. So what happens if you take, say, a glass with water and oil in it, and you shake it all up? Similar to oil and vinegar salad dressing. It starts to just separate out again, right? Well, why is that happening? What if I take one of these non-polar molecules and I stick it in between those water molecules over there? I force it in there. Those water molecules are attracted to each other. They want to stick together because they're little magnets. If I put a non-magnet in between them, I have just created potential energy. Those magnets want to squeeze right back together again and push that non-magnet out of the way. This is the reason why oil molecules don't dissolve in water. Well, why does water molecules not dissolve in oil then? Okay, so say we mix it all up, you got a water molecule floating around up here. Is it particularly attracted to an oil molecule? The answer is no. Now what if it bumps into another water molecule? Their magnets are going to be attracted to each other. And after you get a certain number of water molecules sticking to each other, then the physical properties take over. The density of water is less than the density of oil. So that little water droplet that's formed inside the oil is going to sink down over here and join up with the rest of the magnets. So here's the densities over here. Now, think about the air that you're breathing right now. Nitrogen, difference electronegativity, 0. Same with oxygen. CO2, we just figured out why that's nonpolar. If these are nonpolar as gases and these are nonpolar as a liquid, what is the difference here? And that is simply the mass. These are small molecules over here. Oil molecules are much heavier. 10 to 100 times heavier. That's the reason why. So now we just described why we have water on the bottom, oil on the top, and they don't mix, and why air is on above the oil. It's all density. Now let's look at a molecule called cholesterol. Tell me, do you think cholesterol is a good molecule or a bad molecule?
It's good.
Good.
Cholesterol is the precursor to all your steroidal hormones, including bile salts that you use to digest your food, which is the reason why your liver makes about 1 gram of it every day. So let's look at this. This is the partial structure of cholesterol. Remember when I showed you the partial structure of glucose? What were each of these little bends right here? Those were carbon atoms. We also said that carbon likes to form 4 bonds. Here you see this carbon is forming 4 bonds. Same thing here. But how come there's only 3 bonds right there? It's because they're not showing you the hydrogens. They're leaving out the hydrogens. That's why it's called a condensed structure. But let's go through this molecule. The carbon-to-carbon bond, the difference electronegativity will be 0. The carbon-to-hydrogen bond is 0.35, nonpolar. Look through this whole molecule over here. It's all nonpolar. The only polar part is this oxygen to hydrogen bond right here that I put in red. So think about it. Almost the entire molecule is polar. You got this one small, non-polar, and you got this small polar part over here. What would happen if I took some cholesterol and I put it in this water and oil mixture, I shook it all up and let it settle back out again? Where am I going to find most of my cholesterol? In the water or in the oil? It's going to be in the oil, isn't it? In fact, if cholesterol had its way, this molecule would be right over here where that polar part would be dissolving in the water and the rest of it would be dissolving in the oil. It would form a layer, a monolayer, between the two layers. Okay, now what is the analogy to a cell? The water is analogous to the cytoplasm. The oil is analogous to the membrane. Where am I going to find most of the cholesterol in a cell? It's going to be in the membrane, isn't it? So now we're going into the concepts of biochemistry. Let's look at this molecule right here. So we looked at this before in terms of shape, right? So that oxygen has 4 regions of electron density. 2 have atoms on it, so therefore the oxygen is bent. Remember we went through that? Now what I did is in blue, I put all the polar parts of this molecule, and in black are all the non-polar parts of the molecule. Now let's decide what would happen if we put this molecule in here, shook it up, and then let the oil and water separate out again. About half of this molecule is polar, isn't it? I would suspect it's mostly going to be found in the water, but you might find some in the oil as well. Mostly it's going to be in the water. It's just mostly a polar molecule. So when we use the difference electronegativity, we really create 2 definitions for bonding. So for the sake of naming, for the sake of drawing Lewis structures, an ionic bond is any bond between a metal and a nonmetal, regardless of electronegativity, right? But using difference electronegativity redefines bonding as more precise. So it's possible that a molecule classified as ionic by definition 1 is not ionic by definition 2. So let's not get confused. Naming is in a completely different chapter, isn't it? Before we ever talked about this. When someone asks you to name a compound, they don't tell you go look up the difference in electronegativity. And what's in the same chapter is drawing a structure. So if you're going to draw the structure of sodium chloride, for example, nobody says go look up the difference in electronegativity and then draw the Lewis structure. So don't get those confused, okay? And really what we're doing is simply a convention. It's the convention for this class that we use electronegativity only to look at bonds to find out whether they're polar or nonpolar, to help us figure out is the molecule going to be polar or nonpolar. So I gave a bunch of examples here. So here's some examples of ionic compounds. So aluminum chloride is simply ions, right? Now, here's a metal and a nonmetal. I don't have to go look up electronegativity difference to name it. And I don't have to look up electronegativity difference to say, well, that's the aluminum ion and that's the chloride ion. Same thing over here. Sodium carbonate, polyatomic ion, right? I don't have to look up electronegativity differences to find out that this is the sodium ion. There's two of them, and here's the carbonate ion. And I don't need to look at electronegativity differences over here. It doesn't matter whether that's polar or non-polar. You know why? This is an ion. That -2 charge means that there's 2 electrons more than there are protons in this group of atoms. It's a polyatomic anion, isn't it? And so what about sodium hydrogen carbonate? Okay, well, if I know this structure right here, I automatically know that structure is going to stay regardless of putting the hydrogen on it or not. This group of atoms is extremely stable. By putting the hydrogen on it somewhere, I'm not going to make it unstable. I have to retain this particular bonding pattern. So if I'm looking at this, I'm deciding where do I put that hydrogen? I can't put it here because the oxygen already has 2 bonds. And I can't put it here because the carbon already has 4 bonds. If I were to put the hydrogen here, I'd have to give up that double bond. And I would convert it from planar trigonal into tetrahedral. That's a totally different shape. That's not going to be stable. So just like with naming, if you know the formula for carbonate, you automatically know the formula for hydrogen carbonate. Now when it comes to Lewis structures, if you know the Lewis structure for carbonate, that's not going to change when you put a hydrogen on there. The hydrogen could go here or it could go here, but it can't go here or there. Now, what if I put another hydrogen right here? Now I no longer have a polyatomic ion. So now I have a covalent compound. Its name is carbonic acid. Now let's try to figure out if this is polar or non-polar. So the difference electronegativity between carbon and oxygen is 0.89. Between oxygen and hydrogen is 1.24. So that means that all of these bonds in here are going to be polar. So the question now is, let's see if I can make a molecule out of this. This will work, I think. See if this will work. I know the colors are not good. So here's the carbon. And just say these are all 3 of these are oxygen, right? This looks symmetrical this way. Okay, that doesn't look symmetrical, does it? So now you know that this can move all around like this. These rockets are just moving in all different directions. They're not locked in any particular symmetrical configuration. This is a non-symmetrical molecule. So you have dipoles in here. The dipoles don't cancel out. If you fire these rockets, it's going to go somewhere. It's a polar molecule. Next one is carbon tetrachloride. Let's say the green ones are chlorine. So the difference in electronegativity is 0.61 between carbon and chlorine. So those are polar covalent bonds, right? They're little rockets. But what happens if I were to fire all these rockets all at once? Where's it going to go? Nowhere. It's a nonpolar molecule. Carbon tetrachloride has been used to clean grease off of fine machinery parts, things like that. So if it's dissolving oil off of machinery parts, that must mean it's a nonpolar solvent because it's cleaning off nonpolar molecules off of the metal parts. Now, what if I take off one of the chlorines with a hydrogen? Now, I got 3 rockets and 1 non-rocket. If I fire these rockets, is it going to go somewhere? Yes, it will. It's going to move. It's a polar molecule. So the common name for trichloromethane is chloroform. So chloroform has been used to do all kinds of stuff. In the old days, right? They used to take chloroform, put it on a rag, and you sneak up behind some security guard and you put it over their mouth, and now the guy passes out. So then you rob the bank, whatever, and you go away. What do they do nowadays in movies? Well, they sneak up behind the guy and just snap his neck. Like, have you ever watched Steven Seagal movies? The guy's a total moron. He's like killing all these people with no reason to kill these people. I really wish that he knew about chloroform. So what does that mean? You put it on a rag, you put it over their mouth, it goes into the vapor phase because of the heat of your hand and mouth and all that stuff. You breathe it in. The linings inside your lungs are aqueous, it's water. That means it has to be able to dissolve into the water layer, go through your circulation, dissolve into the tissues of nerve cells, and cause the nerve cells to stop transmitting nerve signals as much. So yeah, it dissolves moderately in water. It's a polar molecule. Now, if I take off another chlorine, replace it with a hydrogen, another nonpolar bond, this is not symmetrical, is it? I got 2 rockets. If I fire them, it's moving somewhere. So this is a polar molecule. If I take off one more chlorine, you put a hydrogen. Now I have only 1 rocket. There's nothing there to counter it. So if I fire that rocket, it's moving. It's a polar molecule.
I think it can be a little confusing, like when we look at the diagrams, because we don't have something physical in front of us. Because the drawings can look very like confusing, you know?
I do know that. Which is more confusing, the 3-dimensional drawings or politics? Okay, so now I took off all the chlorines, right? And guess what? Now there is no rockets to fire. There is no polar bonds here. So this is a nonpolar molecule. Common name is methane. It's a gas. So here's carbon dioxide. We just went through that. What if I were to change one of the oxygens with a sulfur? You see how this is symmetrical? Notice that the bonding pattern is the same because oxygen and sulfur are in the same group. So similar bonding patterns. But now it's not symmetrical. So this one is nonpolar, this one is polar. That's a polar molecule. What about carbon oxide? Okay, if you were to do this and then count up all the valence electrons, you're going to have to put a triple bond in there. There's no other way of doing it. That's a good one for you to try to do, actually. So triple bonds are quite rare. So the shape of this is simply diatomic. There is no central atom. So if this is a polar bond, it would be a polar molecule. If it's a non-polar bond, it would be a non-polar molecule. So the difference electronegativity is 0.89. That means that this is a polar molecule. This is a rocket. That means that carbon oxide is a polar molecule. Now this is totally confusing the students because you know that carbon monoxide is a gas, don't you? Well, let's analyze that a little bit. Carbon monoxide is produced from the internal combustion engine. Inside the engine is extremely hot. The gas fumes that come out of the exhaust pipe are extremely hot. Sometimes there's water vapor coming out of there. What form is the water vapor in? The gaseous form. So the reason why carbon monoxide is a gas is simply because of its origin. Now, this is a pollutant. It combines very strongly with hemoglobin, preventing the binding of oxygen, so it's a toxin. It's produced by internal combustion engines. What happens when it rains? When it rains, this simply washes out of the atmosphere because this is a polar molecule and so is water. So here's ammonia. So the shape of ammonia is I got 4 regions of electron density. One doesn't have an atom, so the shape is that it's pyramidal. If these bonds are polar, it's a polar molecule. If these bonds are nonpolar, it's a nonpolar molecule. But they are polar. So here's the shape of ammonia. It's pyramidal and it's polar. And yes, it does dissolve in water. So Windex is a dilute solution of ammonia dissolved in water. So Windex is, along with some blue dye and a little bit of detergent. So what if I replace the hydrogen with a more electronegative atom, for example, chlorine? Well, look what happens. The difference electronegativity now makes it, these are now nonpolar bonds. Nitrogen trichloride is a nonpolar molecule. It will not dissolve in water.
Why is it considered a non-polar? Isn't 0.12 like still considered a charge? Not a
No,
charge.
it's got to be 0.5 and greater.
Gotcha.
Okay, let me see if I can find something to act like sulfur dioxide. Okay, how about this? So here's sulfur dioxide. Okay, so here's the non-binding electron pair, symbolized by this. Okay, here's the one double bond. Here's the one single bond. So what would the shape of this be? We've got 1, 2, 3 regions of electron density. And the X-ray diffraction machine sees the atoms, but it doesn't see that. So this is what it sees. So the shape of sulfur dioxide is bent, isn't it? It's bent because of this non-binding electron pair. So it's not symmetrical. And these are polar covalent bonds, so that means that sulfur dioxide is a polar molecule. But yet, sulfur dioxide is one of the molecules that can come out of hot engine exhaust or hot earth exhaust called a volcano, and it comes out as a gas. Why is that? It's simply because of the temperature. And here's its close brother. So here's sulfur dioxide. Here's sulfur trioxide. So now the shape is 3 reasons of electron density. They all have atoms, so it's planar and trigonal. One angle is 120 degrees. Okay. And these are all polar bonds. So there's 3 rockets here. If I fire all 3 of these rockets at the same time, where's it go? Nowhere. Okay. So this is a non-polar molecules. Let me see. Okay. So this also comes out of volcanoes and stuff like that. And actually SO2 and SO3 end up causing acid rain from the volcanoes. These are the 2 molecules that give people with asthma problems only because of the acidity. So here's oxygen, it's diatomic. Here is ozone, which is bent. I got 1, 2, 3 reasons of electron density there. So it's bent. Let's see, ozone. That's a hard one. Ozone would look like this, right? So it's asymmetrical, but because the difference electronegativity is 0, it's a nonpolar molecule. You find it as a gas. Then P2O4. Now, the interesting thing about this, or the key to understanding it, is that there's 2 central atoms. God, where do these molecules disappear to? I don't know where they go. They're right here in front of me somewhere. I took it apart. Don't have enough of each color. Okay, so here's P2O4, diphosphorus tetroxide. Just pretend that this is also black like these right here. So you can see that this is central atom has 1, 2, 3 reasons of electron density. So it's planar, trigonal, same thing over here, right? Planar, trigonal. Doesn't matter, you can rotate about single bonds, it's still the same. And these are all polar covalent bonds. So if I fire all 4 of these rockets at once, this thing isn't going anywhere. This is a non-polar molecule. So
Is it considered symmetrical?
I'm sorry?
Is it considered symmetrical?
Yes, it is, right. Mm-hmm.
Okay.
So here's some examples of organic molecules. So organic molecules are those that are based in carbon. And carbon is unique because it always wants to form 4 bonds, and it can join to itself in multiple ways, make an infinite number of different kinds of organic molecules. So here is butane. Here's the molecular formula. Here's a partial structure. Here's the complete structure. So that carbon is bonded to that carbon, which is bonded to that carbon, which is bonded to that carbon. That's how we get this, right? And then every carbon is going to have 4 bonds. So you have enough to make everything saturated with hydrogen. So if you look at the difference in electronegativity, there's nothing in here that's polar. So what do we know about butane? If you look at butane lighters, which I have never been able to find on the internet a decent picture to steal of a butane lighter. I don't get it. But if you look at a butane lighter, it looks like there's liquid in there. What is that liquid? Butane. Because it's under pressure. That's why. Where does the pressure come from? Because these nonpolar molecules are a little bit heavy, but they prefer to be in the gaseous state. So they're trying to evaporate within that container, causing a pressure inside that container. Only so much can evaporate and the rest cannot get into the vapor phase, so it's a liquid. But now when you push down on the button, you open up a hole to the atmosphere, the pressure causes it to come out. And at the same time you push down that button, you strike something, so you cause it to burn with the oxygen that's in the air. So here's propane, similar type of thing. It's like butane, right? You cook with it. Here's a smaller molecule called ethane. So what I decided to do here is just show you a very brief introduction to organic molecules. So notice that these all end in A and E. That means there's nothing in there except carbon-carbon single bonds and no other types of bonds. So 2 carbons in a row is based upon ethane. 1 carbon in a row is based upon methane. So notice this is ethane. I put a double bond in here. It now becomes ethene. Whatever that is, ethene. Okay. So again, it's a nonpolar molecule. If I take another pair of hydrogens off, I end up getting ethyne. The common name for ethyne is acetylene. So acetylene torches and stuff, or a container full of ethylene, there's ethyne in it, and the other cylinder is oxygen. You mix those together, you get an extremely hot torch. Well, what if I put on there an alcohol group? So this is ethane, and alcohols end in OL, so that becomes ethanol. This is also known as ethyl alcohol, which is the older name. Here's the ethyl group, here's the alcohol group. So this is the inebriating liquid. That's commonly drunk, and it makes you drunk when you drink it. Then, if I were to take this functional group right here and oxidize it 1 step, I oxidize this primary alcohol into an aldehyde. So this is an aldehyde functional group right here. So the name would be then F-aldehyde. Put them together, you get ethanal. The common name is acetaldehyde. And you have an enzyme in your body called alcohol dehydrogenase that when this goes into your bloodstream, alcohol dehydrogenase oxidizes it into this aldehyde. And this is the molecule that actually gives you the hangover. So this makes you the happiest guy, the best race car driver ever on the freeway. It makes you able to say the wrong thing to the wrong person at the wrong time in the wrong place. And this is what's going to make you pay for it later. So if you want to get rid of a hangover, what you really need to do is think about how do you get that molecule out of your body. You can sweat it out, you can pee it out. But what does that really mean? Drink water. That's how you get it out. I can take this and oxidize it one more step, and I will get the carboxylic acid. So ethanoic acid is the IUPAC name. The common name is acetic acid. So vinegar is about a 5% solution of acetic acid. And you had to know one of the polyatomic ions that came from this. This is acetic acid. Acids are more reactive, right? If I lose this hydrogen ion right here, I now get the acetate ion. That's acetate right there. So it's a common polyatomic ion because bacteria tend to produce acetic acid during fermentation. And then when that gets into the environment, the first thing it does is get rid of the hydrogen because that's more reactive. And you end up with the acetate ion, which is a fairly stable molecule. Here's another example. This is a nitrile. This makes it a nitrile. And it's got 2 carbons in a row. So the root name is ethane. So the systematic name is ethane nitrile. It's a very, very, very slightly polar molecule. This is 0.49 right here, the difference electronegativity. It's almost polar, almost what we can consider polar, but the difference between 0.49 and 0.50 is insignificant. So this is an interesting molecule because what if you wanted to make a polar molecule react with a non-polar molecule? In order for those things to react, they have to actually come in contact with one another. So the important part of things like nitriles is they can dissolve polar molecules a little bit and non-polar molecules a little bit. You can actually bring them close enough so there can actually be a chemical reaction. And then tetraethyl lead, we talked about it. And so I thought I would give you the complete structure for this. So you see lead is bonded to 1, 2, 3, 4 ethyl groups. So that's where the name tetraethyl lead comes from. We call it an organometallic compound. Okay. But remember, this dissolves in gasoline, not in water. Look at the difference in electronegativity. There is nothing in here that's polar. So why do they put tetraethyl lead in gasoline? This is a very misunderstood explanation for it. But here's what the problem is. Linear molecules burn very rapidly in oxygen. Here's the reason why. You have so many oxygen molecules that can attack that linear molecule. But this is a rather spherical molecule. If you look at lead, you could probably say that it's tetrahedral. So it's getting very spherical. Spherical molecules burn slower. Does that make sense? Here's the reason why they have what's called high octane fuel. Is to prevent what's called pre-ignition. So what's supposed to happen is gasoline is sprayed into the cylinder. either leaked through a carburetor or sprayed with fuel injection, whatever. It's vaporized into the cylinder. It mixes with oxygen from the air. Then the spark plug ignites, causing it to explode. Pre-ignition is when the engine is so hot that you spray your gasoline in there and the heat from the engine itself makes it blow up before the spark plug goes off. So that causes your engine to basically ignore all the timing and everything involved in it. So the timing of the cylinder is going off just right time, right? So it causes your crankshaft to not go smoothly, but just bounce between different explosions. And it beats the heck out of your bearings and everything else. It won't run smooth and you won't get good efficiency. So they would put tetraethyl lead in there to make it burn slower, even at a higher temperature, so you avoid pre-ignition. Well, anyway, they used leaded gasoline for decades and decades, and then somebody came up with the idea that, oh, lead is a bad molecule, or bad element, I should say. Lead makes babies retarded. Okay, well, I thought babies came retarded. Anyway, there were examples of lead-based paint, children eating lead-based paint and getting into the food supply, whatever, and it does cause neurological damage. So lead was banned. So they replaced it with a molecule called methyl tert-butyl ether, MTBE. So here's the structure of methyl, and this is the tert-butyl. And when you have a carbon oxygen to a carbon, that's an ether. So methyl, tert-butyl, and it's an ether. And here is the structure of it. Okay. And you can see it also is spherical. You guys following that? So what they do is they take crude oil and they refine out by temperature gradient and evaporation and stuff like that, different sections of the crude oil. So when they get the part that's good enough for an internal combustion engine like a car, they put it into experimental engines. And so these engines will be able to measure the knock that's coming from these engines. So they want to get rid of the knock, and so they add this compound, MTBE, until you get to a certain octane rating. So how do you increase octane rating? Not with octane. You increase it by putting in MTBE. So does higher octane give your car automatically more miles per gallon and more power? The answer is no. So what you should do is look at your manufacturer's recommendations and decide how much money you want to spend on the gasoline. So the octane rating is basically two types of measurements divided by 2. They take the average, and it's simply to do with engine knocking. So if your engine runs hot, if it's a race engine, if it's some kind of high performance engine, you need high octane because it's hot and you will get pre-ignition. But if your engine is not running hot, then you should use the cheapest fuel that you can in there. Otherwise, you're just throwing away money. The difference between regular and Supreme is like, what, 15 cents a gallon? What is you paying for? You're paying for this molecule. This molecule is extremely easy and cheap to make. So the gasoline manufacturers and sellers are making a lot of money off of this molecule. A lot of money. You should do your best not to give them your money. So again, if you just have a regular car, you do not need to put high octane in there. It's not going to do you any good. Let's see. So according to the AAA, in 2015, 16.5 million drivers spent $2.1 billion unnecessarily on premium gasoline. Save your money, please. So this is a very important exercise I hope that you will do. The lesson is count up your valence electrons very carefully. Otherwise, you'll be thrown off. If you look at sulfur trioxide, right? 24 valence electrons, you have to end up putting that double bond there to make sulfur happy. It's a sulfite ion, there's 26 electrons. There's 2 electrons more that came from some metal or somewhere. So you have 26 valence electrons. You do not need to put that double bond there. This is planar trigonal and nonpolar. This is pyramidal and it's ionic because of this. So yes, we do have some exceptions. One exception is radicals, okay? So nitric oxide is a radical. It has an odd number of electrons, making it very reactive. Here is one scenario where it can react with oxygen and you get rid of the radicals. So you got 2 of these with 1 of these, and you make as an intermediate these 2 radicals right here, the nitrogen dioxide radicals. But then these 2 odd electrons form a bond. Now you have a stable molecule, nitrogen tetroxide. You also have some molecules that are not symmetrical. So dinitrogen oxide is known as nitrous oxide or laughing gas, and there's nothing you can do to make it symmetrical. So they use that in dentist's office. I had one dentist that gave it to me one time and I was not laughing because there's absolutely nothing funny about going to the dentist. Then we have some molecules that do occur and they're electron deficient. For example, borane. This is known as borane. So boron trihydride. If you look at on the periodic table, borane is in group 3. So there is no way that you can get more electrons from here. But this molecule exists. It's not stable. But if you make it and you keep it in a container away from any other things, it will stay there forever. But what does that boron want? 2 more electrons to call its own, so it can be like a noble gas. So it can take what's called the hydride ion, and now you form boron tetrahydride. So wait a minute. Is this stable? No. Is this stable? No. So if you put either one of these out into the atmosphere, it's not going to last. But that's the purpose of having these kind of molecules that are not stable. They become tools for us to make other things. If I make boron tetrahydride, for example, I can put it in with another molecule, and this is going to give the hydride ion to that other molecule, reducing it, and I'll end up making this again. Or I can take this and put it in another molecule, and it would take the hydride off of it to form this. But whatever, I'm using it as a tool. It's a very reactive molecule that forces other molecules to go under chemical reactions. It's a tool. Then we have some that have what's called an expanded octet. It's like, what the heck? Yeah, I had that same problem with it. So here's a molecule that does exist. We'd have to keep it in a test tube away from other things. The central atom has 2, 4, 6, 8, 10 electrons around it. Oh my God, it doesn't meet the octet rule. So you're not going to find it floating around outside your apartment. But if you make it and you keep it away from other stuff, it will last a very long time. It's not stable, but we use it to put chlorine atoms on other molecules. That's what it's for. Again, you're not responsible for these exceptions. And then we have metals that have moderately high electronegativity values, and they often form covalent bonds. So remember, our convention for this class, if you see a metal and a non-metal, what are you going to do? You're going to do it like this, just like how we name it. But what if you're cruising around the internet and you see this? I have to make you ready for that. So if you look at the difference in electronegativity between lead and chlorine, it's 0.83. So if you're looking at electronegativity, this is more accurate than this. But then there's a problem with this. Why would it do this? Is it meeting the octet rule for lead? No. So my issue with it is it doesn't get you any further towards an understanding of anything. That's why I just chose, we're just simply going to do it this way. You do the Lewis structure for lead 2 ion, you do the Lewis structure for a chloride ion. Simple as that. So here's some common mistakes. It's like, here's what not to do. So what's wrong with this? Non-metal, non-metal. Why would you make an ionic bond between non-metals? We're not going to do that. And here, what's wrong with this? Oh, they didn't put all the dots in there. What's wrong with this? We're not going to make a covalent bond between a metal and a non-metal. What's wrong with this? Oh, it's not symmetrical. Same over here, this is not symmetrical. And besides that, hydrogen can never be a central atom because it only forms one bond, because it wants to go from 1s1 to 1s2. Again, not symmetrical. Also, fluorine does not form 2 bonds. Look on the periodic table, it's in group 7. It wants to gain 1 more electron to become s2p6. What's wrong with this? Well, we didn't satisfy the octet rule for sulfur. So you need to make a double bond somewhere. What's wrong with this? Well, what's wrong with it is that the students didn't count their valence electrons correctly. You do not need to have a double bond there. What's wrong with this? Fluorine does not form 2 bonds. It forms only 1 bond. This is more correct for this one, except the student didn't put dots around the fluorines. What's wrong with this? Again, group 5, you lose 3, you still got 5 dots around it. What's wrong with this? Okay, hydrogen carbonate has to maintain its structure. Here you changed it. Here's what hydrogen carbonate should look like. Okay. So that's wrong. This is wrong because carbon doesn't have octet around it. You got to make a double bond either here or here. This is wrong because oxygen doesn't form 3 bonds. This is wrong because students who put something like this probably didn't read any of the chapter. They think you just throw stuff together and it automatically looks cool. And here, this student invented their own polyatomic ion. And again, I don't want to suppress your creativity, but if you want to be creative, take an art class. If you want to learn about the world around you, then you take a science class. If you're a scientist and you need to figure out ways to understand the world, you have to come up with experiments and stuff like that. Then you have to be extremely creative to come up with those experiments. So this is correct, but people would look at that and say, oh, it's linear. It's not linear. Okay. Same thing here. So this is bent with 109.5 degrees. This is bent with 120 degrees.
If it were linear, you just have one bromine atom?
No, that would be diatomic. If that valence, if that non-bi-electron pair wasn't there, then that would be linear. But you got 1, 2, 3 regions of electron density that all push each other apart.
I meant for the bromine sulfur. I thought
Okay, let me just put this together real quick. It would look like this. See that?
yes,
So those 2 non-binding electron pairs push the other ones down.
I see.
That's why it's bent.
And if there was only one bromine atom, what would that look like?
That would be diatomic.
Diatomic.
Yeah. You're talking like this, right?
Yeah. Oh, I see.
Yeah.
Because there's the other electrons are out there.
Yeah,
Therefore, it's not linear.
Well, there's no central atom.
Okay.
Yeah. And then when we get to chapter 11, we're going to be looking at resonance structures. And resonance structures, you're moving electrons into double bonds and you're putting them into different places between different atoms. So here's that situation. I could have put this double bond here or here. Okay, so this is one resonance structure. But what I cannot do is move atoms around. Okay, by moving atoms around, that changes everything. So they're not resonance structures if you move the atoms. And we'll get to that in chapter 11. So anyway, I just really like this cartoon. It's chemically wrong. This is acetone right here. And this looks like some form of Coulomb's law. And anyway, so he's very happy because he's made all of his atoms happy by because of the octet and duet rules. But I just like the look on his face. He's very happy. And then scientist humor is the best. Get it? Wet floor, molecules. Brings me to something I want to point out. Just because you're a smart person, you know chemistry does not make you a good chemistry teacher. So here's what they're trying to show you for water molecules, right? You don't know how mad I get when I have to spend all this this money on models, and they send me stuff like this where there's no other holes right here. This is undoing what I'm trying to teach you. Why would these two molecules, these two bonds right here be at that angle to each other? There's nothing here to repel them down. This should be linear. So they don't give me red ones that have 4 holes in it. This is what water should be doing, not this. This is anti-educational, and I'm forced to buy them. Anyway, so here's the structure of methamphetamine. So what is methamphetamine? This right here is an amine, it's amphetamine. And when I put that methyl group on there, it now becomes methamphetamine. Okay. And so why am I showing you this? Because that carbon has 4 regions of electron density. It's tetrahedral. That nitrogen has 1, 2, 3 regions of electron density. So it's planar trigonal. This actually has 4. They're not showing the hydrogen. They're not showing 2 hydrogens. They're not showing any of the hydrogens over here. That's tetrahedral, 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 all tetrahedral. Okay. And I want to show you this chemical structure over here because people see it all the time and they automatically look at this molecule, which is known as benzene, which is actually not a very common arrangement. And they do all kind of stuff where they're trying to make everything cyclic. Most things are not cyclic at all. So when people see this, they think, oh, it looks cool, and they try to make Lewis structures that are cyclic when they're not supposed to be. Anyway, did you guys all see Breaking Bad?
Yes.
To me, that was one of the most amazing stories. I put it right up there with all the classics like Gone with the Wind or anything like that. I thought it was an amazing depiction of how somebody can basically break bad. It's amazing.
Do you ever get tempted?
Oh, I've had some stories about that. So, you know, I'm born and raised here, so I know a lot of people that do a lot of different things. And one friend called me up one time and he goes, "Oh, Harry, I got to talk to you about something." I said, "Okay, talk." "Oh, we can't talk over the phone." I'm like, "What?" So we go and we meet at this restaurant upstairs and everything. And it's like trying to tell me that, you know, I heard you were making drugs for the so-and-so family. And I'm like, no way, I'm not. He goes, well, I just don't want you to know. I don't want you to get in trouble and all that kind of stuff because those guys will throw anybody under the bus. I said, yeah, forget it. But it was kind of funny that he heard that from somebody.
That's pretty funny.
I was a faculty senate chair for 4 years, and for 3 of those 4 years, I ran the all-campus council of faculty senate chairs. And our meetings were always attended by a vice president and oftentimes by the president. And one time we're all in there, and so we're talking about what can we do to get more revenues for the university. And I said, well, I'm a chemist. How much money do you need? And they slowly got the idea what I was talking about, but yeah, it's kind of funny. So I know this is going to take a while for you to sink in. Chapter 10 has a lot of different things in it, and I'll be looking forward to tomorrow when we start on another chapter, but I'm going to ask if you have any questions about this chapter because it is a lot of stuff in it. So we're 6 minutes over already. I should probably just stop it. Does anybody have any questions? If not, I'm gonna end this thing and make sure if you're in Biochem 241, you got today and tomorrow to take exam 2, right? And then if you're in Chem 100, your exam 2 doesn't start until next week, Monday and Tuesday.
Will Chem 100 have their review on the material?
Thinking about it. We'll see.
Okay.
Yeah.
Was the review recorded? I wasn't able to attend today.
Yes, it was. Yeah.
Okay, great. And then
I
tomorrow
threw it
morning.
up- I threw it up there, but I haven't had a chance to check to see whether it finished uploading or anything.
Okay, thank you. And then tomorrow morning, do you want us to email you if we're taking it tomorrow, or will you just send the code out to everyone?
I'll probably just send it out to everybody because that's their last chance anyway, right?
Okay, thank you.
Okay. Okay,
Can I-
so.
Can I
wait,
talk to you after?
yeah, sure. Go ahead.
No, I mean like after like class.
Oh, yeah, I just saw your chat, yeah. Okay, so I'm going to, I don't know if I can end this for everybody or anyway, so I'm gonna just say goodbye to everybody except one person has some questions afterwards. Let's see if they just check out on their own.
Well, yeah. Anyways.
See if I can. One more. I
Are
think
you-
it works.
Are you gonna record my question?
No.
I mean, it's something